Hello friends, in this video we will learn about how to calculate reliability and safety margin of an infrastructure. So if you consider any infrastructure or system or an asset, it degrades over time. Basically its performance not remain same as was it in case of brand new. This happens because of loading condition, environmental condition or time dependent degradation that happens into the system. So due to this, the system performance decreases with time. So question is, how do we know that the system is performing well under given constraint at a given point of time? So, a structural safety is an important concept for any engineer, and a structural safety depends upon two things. One is what is the load that is applied to the system, and what is the capacity that we have of that system. Now, how we calculate this demand and capacity of the system? So at any point of time, we cannot calculate what is the exact maximum load that is coming to the system and also what is the exact maximum capacity of that system. We can always have some uncertainty. So load and the resistance can always be given in terms of uncertainty. So we can basically say in terms of chance of risk. We can talk in terms of probability. We cannot say something like exact or deterministic. In other words, safety or reliability can always be given in terms of probability. It cannot be given in terms of deterministic quantity. So let us discuss more about how we calculate reliability of a system. As I said, calculation of reliability involves two things. One is what is the load that is coming to the system, that is demand, and what is the resistance that system can provide, that is capacity or supply. So let us say X denotes supply, that is capacity of the system, and Y denotes demand, that is what is the load that is coming to the system. So basically this is a question of supply or capacity and demand. In this case both are uncertain. So X and Y both are random variables. So now using these two variables, that is X and Y, in terms of demand and capacity, we have to calculate reliability or safety of margin or probability of failure. So the objective of reliability analysis is to ensure that X is greater than Y. X is basically capacity, that is my resistance provided by the system should always be greater than the demand, that is the load coming out to the system. So this is the criteria, that is my capacity should be greater than the demand throughout the useful life or some specified time. So the time period in which we are interested for any engineering system. This assurance is possible only in terms of probability. So we can talk in terms of probability. P X is greater than Y. What is the probability that my capacity is greater than the demand? Now this probability represents a realistic measure of the reliability of a system. So we will say the probability is a measure of reliability of that system. Other event, that is 1 minus probability of reliability, is basically probability of failure. So the probability of complementary event, that is X is less than Y, is basically corresponding measure of unreliability, often called probability of failure. So the question is how we calculate the probability of failure. That is probability that X is less than Y. Now we will use total probability theorem to calculate this probability, that is probability of failure. And this total probability theorem is illustrated in this figure. So let's say we have an event A and the whole sample space can be divided into different segments, different events. So let's say we have B1, B2, B3 and B4 events. In general we can say BI. So now I can calculate probability of A by first calculating the conditional probability, that is probability of A given that BI has already occurred, and then I have to multiply the probability that event BI will occur. So this is the thing that we have to use, and then we have to sum over all i's to get the probability of A. So this is the summary of total probability theorem. So let us use this to write expression for probability of failure. Let PDF for random variable x and random variable y or fx and fy are known to us. Then we can calculate probability of failure. That is probability that x is less than y. So we will use total probability theorem to write this expression, and we can write probability that x is less than y given that y is equals to a small y, and then we have to multiply by an expression, that is probability that y is equals to a small y. Now if you see the first term, that is probability that x is less than y given that y is equals to a small y, is nothing but CDF, and this CDF is evaluated at a small y. So we can write this is a CDF of x, random variable x, and evaluated at a small y. So this is for random variable x. And then I have to multiply by term probability that y is equals to y, and then we have to also sum over all y. So this is the expression for probability of failure in case of my random variables are discrete. Now the question is how we calculate this probability of failure when y becomes a continuous random variable. So this is the expression that we have in the earlier slide. In case of continuous random variable, I can write my expression something like this. Now if you see this expression and compare with the previous expression, we can see the first term is same, that is CDF of x evaluated at a small y, and the second term becomes fy dy. We also have one difference, that is summation is now written in terms of integration. So we can illustrate this term using this figure. So if you see, we have to calculate probability of y that is equals to a small y. Basically we cannot calculate point probability. Point probability will always be 0. So we consider a small interval of delta y. Now if I see what is the probability in this interval, that is probability that y, random variable y, that is y lies between y and y plus delta y. So this is nothing but this area, and we can write this area. If I assume the ordinate remains constant, then I can write this area is nothing but fy times delta y. And in case of limiting situation, when delta y goes to 0, this delta y becomes y, basically dy. So I can write my probability py something like this, and summation becomes integration in this case because my variable is a continuous random variable. Basically we can show this expression geometrically also. So this is the same expression, and this expression, that is the probability of failure, is basically convolution with respect to y. So let us illustrate using a diagram. So in this case, this denotes PDF for random variable y, and this curve is PDF for random variable x. X is my capacity and y is my demand, and the corresponding PDF is fx and fy respectively. So if you see this term, that is fx evaluated by, is basically cumulative density function, that is CDF. So let us say if I consider a point y here, that is random variable y takes a value of y, then I can go to curve for random variable x. So this is random variable x curve. So this fx, that is CDF, is nothing but this area. So this is the first term of the integration. Now the second term, that is fy dy, is basically area of a rectangle. So let us say we can show this here. So this is my y curve. So I can show this rectangle something like this, and this distance is nothing but dy. So this is the second term, that is fy dy. So if I multiply these two terms and integrate from 0 to infinity, this will give me the corresponding probability of failure. Basically, the probability of failure can also be given qualitatively in terms of area under curve between the two curves basically. So the probability of failure depends upon the overlapping region between fx and fy. So this is my fx and this is my fy. So this area, that is overlap area, is a qualitative measure of probability of failure. So same is written here. The overlap between fx and fy represents the qualitative measure of probability of failure. Of course, this overlap area will also depend upon the relative position of this curve and this curve. So that is, what is the effect of relative position of fx and fy on probability of failure, that is pf. So let us say in this case I have this curve, and this is a qualitative measure of probability of failure, and this is corresponding position for the mean. So this is mean for y and this is mean for x. So let us consider the first position for mean for random variable x. In that case I have this area. Now if I shift my x curve, that is PDF for x, then I have a different mean. In that case, this is the region of overlap I have. So basically you can see this region has reduced. So I can say in this case probability of failure is less. So we can say as the two curves become further apart, the probability of failure, that is PF, decreases. So this distance, as this distance increases, the PF basically reduces. So if you have two curves, that is demand and capacity, are very far away, in that case basically you will have zero probability of failure. But that is an ideal situation. Now the question is how we measure the relative position of these two curves, that is demand and capacity curve. So the relative position between fx and fy may be measured by, so there are two possibilities. The first is we can calculate the ratio mu x by mu y, and this is called central safety factor. So one way to measure this dispersion or this relative distance between two curves is by calculating mu x divided by mu y. Another way, we can also calculate what is the difference between mu x and mu y. So this is called safety margin. So either we can calculate central factor of safety or we can calculate the difference, that is safety margin. So we can say that probability of failure depends upon the relative position of demand and capacity curve. The probability of failure also depends upon the dispersion of curve, that is how these curves are flat or spiky in nature. So what is the effect of dispersion of fx and fy on probability of failure? This is illustrated in this figure. So if you see, in this case, I have a qualitative measure of probability of failure is this area. Now let us make these two curves little bit flat, that is diffused. So now if you see the dashed curve, so this is the fy and this is fx. In the second situation, my area has increased. So you can say as you increase the flatness, you will have more probability of failure. So probability of failure increases with increasing dispersion of the curves. So the overlap region also depends upon degree of dispersion of fx as well as fy. So we can compare the overlap of solid curve in this case and the dashed curve, and we found that the dashed curve has more area in this case, and this means the probability of failure will be high for the dashed case. So this dispersion may be expressed in terms of coefficient of variation. So we can express coefficient of variation for x, that is sigma x divided by mu x. Similarly, coefficient of variation for y, that is sigma y divided by mu y. So in summary, basically we can say probability of failure is a function of mu x divided by mu y, as well as this is also a function of coefficient of dispersion. So this is related to relative position and these two are related to dispersion of the curve. So to summarize, we said we have two random variables x and y, that is demand and capacity, and the overlap between these two PDFs is basically probability of failure. Now one way to calculate this probability of failure is in terms of safety margin. The advantage of calculating the safety margin is we will have only one random variable. So safety margin M is defined as x minus y. X is basically a capacity and y is the demand. Now x is a random variable, y is a random variable, then M, that is safety margin, will also be a random variable. So M is a random variable with corresponding PDF FMM. So let's say this is the corresponding PDF for safety margin. Now failure will occur when M is less than 0. So this means x minus y is less than 0, that is x is less than y. This means my capacity is less than the demand. This means the structure resistance is less than the load that is coming to the structure. And probability of failure can be given by this expression, that is Fm dm minus infinity to 0, and in terms of cumulative density function of M, we can write simply Fm evaluated at 0. Now you see the advantage of introducing safety margin is that now we are dealing with only one random variable and that random variable is M. We don't have to bother about x and y. So let us illustrate this using a graph. So this is PDF for my new random variable M, that is the safety margin. And now in this case, whatever that is coming to the negative, that will contribute to the probability of failure. So this area basically corresponds to probability of failure. So this means if I integrate from minus infinity to 0 of this PDF, I will get corresponding probability of failure. Or in short, we can simply write this is nothing but CDF evaluated at point 0. Let us illustrate this using an example. So consider a structure whose strength is R, that is a normal random variable with mean mu R and variance sigma R. Similarly, the load is also a normal random variable with mean mu q and a standard deviation sigma q. Now we have to calculate probability distribution for the safety margin, and we have to also calculate corresponding probability of failure. So now as I introduced, the safety margin is given as x minus y. X is my capacity and y is the demand. In this case, capacity, that is the resistance, is R, and the demand, that is load, that is Q. So we can write my safety margin equation M, that is R minus Q. Now we can also calculate what is the mean for this random variable M, that is the new random variable. If you remember, we have discussed already, if this is normally distributed and this is also normally distributed, then we can write mean for corresponding function, in this case mu M. This will be nothing but mu R minus mu Q. And we can also write sigma M, that is nothing but a square root of sigma R square plus sigma Q square. And we are making one assumption in this case, that is R and Q are independent to each other. Now once I know mean and a standard deviation for this safety margin M, we can calculate the probability of failure. So this is the safety margin. And what was the first step for calculation of probability of failure? That is, we have to normalize the random variable M. And if you remember how we normalize any variable, that is x, if I have a random variable x, then I subtract the mean and divide by a standard deviation, then I get the normalized random variable. So this is the common procedure that is used for normalizing a random variable. So in this case, I will have, in place of x, my random variable is safety margin, that is M, and mu M we already know and sigma M we already know. So we are interested to calculate value of Z when M is equals to 0, because at that point of time we can calculate the probability of failure. So if you remember, we said probability of failure is nothing but this CDF of M evaluated at 0. So we can plug M is equals to 0, and corresponding Z value is nothing but minus mu M divided by sigma M. And graphically this is illustrated here. So if you see this graph, I am interested to calculate this area, and this area is nothing but a standard normal distribution. Tables gives you this value, so that is phi Z value. If you see any standard normal distribution table, that will give you this area, that is phi Z. In this case, Z will be minus mu M divided by sigma M. So phi Z is probability of failure, and Z value is nothing but minus mu M divided by sigma M. So we can write PF is equals to phi minus mu M divided by sigma M. So if I use properties of normal distribution curve, we can write this is nothing but 1 minus phi of mu M divided by sigma M. We can also calculate reliability of the system, which is basically equals to 1 minus probability of failure. And probability of failure we have already calculated. So if I write 1 minus probability of failure, so this will be simply phi mu M divided by sigma M. So this is basically probability of failure, and this is 1 minus phi Z. So this part of the area is the reliability. So in this video, we have seen how we can use total probability theorem to derive expression for probability of failure. And once I have probability of failure, This can also be used to relate with safety margin. In the next video, we will see one another important concept that is used to assess the reliability of a system, that is called reliability index. For the time being, we can stop here. See you in the next video. Thank you.